Today I would like to tell you about some technical theorem involving the integer grid in the plane and the area of empty triangles defined by this grid. And this theorem is curious and interesting on its own merit, but it has some surprising applications which I hope to record video on later on. So this is more of a curious theorem and its proof, and I hope it will be interesting on its own merit. So we are dealing with the integer grid, namely the set of all points that have integer coordinates in the plane, and we are interested in grid triangles. Those are triangles where their three vertices are integer grid points. Right, now we're interested here only in triangles that have non-zero area, so the three vertices are not all collinear. And in fact, if you look on the example here, the green and the red triangle have the property that the only grid points they have are their three vertices, while the yellow triangle have a fourth point that is on its boundary. We consider the triangles to be closed, so we will consider the yellow triangle to have 4 grid points in it. And triangles that have only only the vertices are grid points, we will call them fundamental triangles. And fundamental triangles are surprisingly interesting because what you can do with a fundamental triangle is you can rotate it by 180 degrees and translate it and glue it to itself, and you get a parallelogram, surprisingly enough called the fundamental parallelogram. And then you can repeat this gluing process, right? Take the parallelogram, glue it to itself, repeat, and so on. And you get the tiling of the plane with these fundamental triangles. So this tiling covers the plane. And if you think about it a bit, you would realize that all the vertices of this tiling must be the integer grid points, and since it covers the whole plane, it must be that it covers all the grid points. Namely, this fundamental triangle spans the grid, which is kind of a very nice property, and it's essentially a unique property of these triangles. Okay, so a quick repeat of what I just said. So a triangle is a grid triangle if all its three vertices are integer vertices that belong to the grid, and a grid triangle is fundamental if the only grid points in it are its three vertices. And I would like here to show the following theorem, which says that a grid triangle is fundamental if and only if its area is half. So this is kind of surprising. It says that all those fundamental triangles have the same area. They might be very long and skinny, but they always have area half, and you cannot make them bigger, which is what I would like to show, which is as I said, I believe an interesting result on its own. I'm not aware, I don't think this theorem has a name. It might be considered to be a special case of a theorem I will mention later on. Okay, here's another tiling of the plane by such a fundamental triangle. And the idea is to look on one of the grid points and all the triangles in the tiling that touch it. So if you think about it a bit for a second, you realize that there are 6 such triangles. And what we're going to do, every triangle is going to charge itself to its bottom left vertex, right? So this grid point in the middle is going to be charged by this blue and red triangle. By the way, notice that all those triangles in the tiling have the same area. They are copies of the same, translated and rotated copies of the same triangles. Of course, they have all the same area. So, as such, every grid point would be charged twice. Or if you want, every grid point would be associated with 2 copies of the fundamental triangle. Now, the key observation is that every grid point corresponds to one unit of area. And the easiest way to say it is just think about back to the regular integer grid. It defines a natural partition of the plane into unit squares. And now, again, associate or assign every square to its bottom left corner. Right? This is the vertex of the integer grid. So every integer grid gets assigned one unit square, and it gets two fundamental triangles assigned to it. Since the two fundamental triangles have the same area, it follows that fundamental triangle must have area half. So we proved one direction of what we wanted to prove, that if a triangle is fundamental, then its area is half. To prove the other direction, it's not too difficult. One just needs to be careful. And we will first prove a Har-Peled lemma that if we have a grid triangle and it contains more than 3 grid points, then it must contain a subtriangle, a triangle that it's properly contained in it, that is a grid triangle, right? And that, of course, is not hard to see, right? Because if you have a triangle a grid triangle, right? So the 3 vertices are grid points, and there's some grid point inside. If it's in the interior, you can just partition the triangle into 3 triangles. So 3 triangles are grid triangles, and the claim holds. The other possibility is that the fourth point, is on the edge of the grid triangle, but then you can partition the triangle into 2 sub-triangles. Both of them are grid triangles. So this lemma holds. And this lemma is interesting because what it says is that you can continue in this fashion, right? As long as you have a grid triangle that contains more than 3 points in it, you can find a sub-triangle that is strictly smaller than it contained in it, and you continue in this fashion until you bottom out. And you have to bottom out because every time you go down, the area shrinks, right? And it shrinks until you bottom out with a fundamental triangle, a triangle that contains only 3 grid points. If you don't buy this argument, you don't want to think about it as area, just think about how many grid points your triangle contains, right? Every time you do this, you apply this lemma, the triangle contains fewer and fewer grid points until you reach the triangle that contains only 3 points. So that implies that every triangle that is a grid triangle by necessity contains a fundamental triangle that is a subtriangle of it, and it's fundamental, as I said. Okay, so now we can prove the other direction, because if I give you a grid triangle of area half, either it's fundamental, and then we are done, or if it's not fundamental, namely it contains more than 3 grid points, then the corollary above tells us that it contains a subtriangle that is fundamental. This subtriangle has area strictly smaller than half, but we already proved that a fundamental triangle has area half. So that's a contradiction. We conclude that if a grid triangle has area half, then it is a fundamental triangle. Namely, it contains no other grid points except for its 3 vertices. So this is the theorem that we just proved. If we have a grid triangle, then it's a fundamental triangle, if and only if its area is half. So the applications. So one nice application is peak theorem, which I hope, as I said, to make an independent video about. Another application, which is much more surprising, it turns out that this theorem has connection to number theory, to what people refer to as the geometry of number. Thank you.